Last time they fluoresced also. I think after this one,
So do you guys have any were there any questions on the homework thing or yeah.
For number one, we're having trouble figuring out why something with using good solvent, why that's beneficial.
I think it was why the UV causes it to stretch out.
Let's see. Curing it in a good solvent increases the size of the chains, while curing the copolymers.
That was the toluene versus
Acetone.
yes.
Yeah. So basically, yeah, he shows that in scheme one. So
yeah, my question was, why does the UV cause the chain to get longer in the good solvent?
all right, so he takes it in the good solvent, and then he's going to bond these groups together, these biphenyl groups. That's like if you just take that molecule alone, that's a UV initiator, a free radical. It's like if you zap that thing, it makes a free radical. I think this comes off somehow. It makes, and you get a free radical on the aromatic, and then that attacks. I guess the two free radicals can combine to bond, so basically those things just link together. So when it's open like that, then they're going to link in short contour lengths apart. It's driving along a little curvy road, it's going to be things that are like right after each other. Whereas if you put it in the poor solvent, it's already phase separated, it's already collapsed. And these groups are soluble in the acetone, and the main chain isn't soluble. So those things are going to have to stick out. So they won't be in the middle. And he shows that with some other measurements later on. And then when he cross-links them, they're going to be like this one and that one will cross-link because the things collapse down. Like, in other words, things that are a large contour length apart will bond together. So then I think on the step how large the things are. Like afterwards, he's going to put these into a pore solvent and then to measure the size. And then the size of this thing's going to be larger than that because this thing's glued together into a small ball. That one's going to be kind of globular. There's a blob here, a blob there, and then a loose chain in between. I think that's what that's. Use scheme one. I just used scheme one. I just did what you're supposed to do. So, I mean, you might want to read it a little bit to figure it out. That's kind of the gist of it, I think. I mean, like this is a UV, or this is a UV curing. Both the purple things are UV curing. So he starts with open chain, closed chain, and then when you UV cures, you get a smaller thing here. So he talks about increases the size. Yeah. So he talks about this in terms of the molecular weight because it's the equivalent. So the equivalent polystyrene molecular weight for this object is going to be a short chain. The equivalent polystyrene molecular be a longer chain. So he says, like, in the measurement, like this has a higher molecular weight than that one, but it's the same molecular weight, starting with the same polymer. So if he had done light scattering detection, he would have seen that. That would give you exactly the molecular weight, not the hydrodynamic size of the thing.
And that kind of ties into part B.
Yeah.
They had a better
GPC.
yeah, the better GPC. Point 3. You had a better GPC, you would have been able to compare multiple tests.
Yeah, like Neil Ayers in chemistry has a GPC that we use that has 3 detectors on it. It has index light scattering and viscosity. And then also like the molecular weight for those three should be exactly the same number because it's in a small fraction, the different moments of molecular weight are the same value if it's monodispersed. So once you so if they aren't, then you know that it's got some other story to it, like it's this branched sphere thing or some other branched polymer or something else going on. So, but the light scattering will give you the molecular weight, like the actual molecular weight. Anyway, anything else? There's one other, anything else on the questions in this? Yeah. Here, all right. So, all right, so he's got the, he's got that scattering business. So he shows this weak slope. So the intensity is like the mass, kind of proportional to the mass. And this is 1 over the size. You have a fractal law, the mass goes with the size to the fractal dimension. So if it's a rod, it'll be to 1. If it's this random walk, it's to the 5/3. And if it's a 3D, it would be like 4 actually here, because you go to the surface scattering, because of the, you don't get scattering from the bulk when it's 3D. So anyway, so 1.7 matches up with the prediction for good solvent chain. So that's what's going on there. And then the steeper ones mean that it's a solid object. Like if it's above 3, it's a solid object. If it's not 4, there's a rough surface to the solid object. And there's called a surface fractal dimension, which is 6 minus this number. So it'd be like 2.7, which tells you how rough, like an AFM will give you a surface fractal dimension. It's got to be how rough the surface is. In other words, if you have so Mandelbrot wrote a book called Fractal Geometry of Nature in like 1970 or something. And then the idea is he started out with the coastline of England. I think he was in England at the time. Anyway, so if you measure the coastline of England on a large scale, you get a small number. And if you zoom in more and more, you get a bigger, larger and larger number. And if you go down to like 1 grain of sand, it's almost infinite. But that's how he starts that book. Anyway, so that's like a 1D fractal. In other words, it doesn't have a smooth surface. If it had a smooth surface, then the coastline would be the same number no matter what size scale you looked at it. And then you can also do that in 2D, like on a surface. So you can have a surface fractal, and a solid one would be a fractal dimension of 2. Then ones that have a rough surface, the dimension goes up, meaning that depending on the size scale you look at, it has more and more surface area. Anyway, so that's what 6 minus this 3.3 gives you 2.7, which would be the surface fractal dimension of the thing. And if it was 2, it'd be 6 minus 2 would give you 4. It would be 4 if it's a smooth surface, and that's kind of how that thing works. So this is a rough surface. Anyway, and I can later on, maybe I'll show you how to get that law, but basically that's how to look at these. So you look at a log-log plot, you're looking for the slope, so you get the power laws. You're looking for a 4 and you're looking for a 2. And if you find the 2, this end of the 2 is the coil, and that end of the 2 is the like the monomer, or whatever sub particles making it. When you find 4, that's a surface. The 4 ends at the particle size. Like 2 pi over that Q would be the particle size. So basically that's scattering in a nutshell. Then how do you get that? I went through it and it says derive this. Floyd-Kriegbaum is done in class. So I did that. Oops. I guess that works on this too. I did that. That's just the Floyd-Kriegbaum derivation thing. So up after that. This is it. Just copy this. So this thing is the probability. The probability of finding end-to-end distance R. And if you multiply that by R squared and integrate it, then you get the NL squared answer. And then if you modify that for self-exclusion, then you end up with this expression, which can't be integrated. You can integrate it numerically, but you can't integrate it straight to analytically. But you can do a derivative of it and find where the peak in that curve would be. So you do that, then you get this equation, set that derivative to 0 to find the peak. and then just rework this into terms of the normal coil size and this expanded coil size. And then drop off the 3 term, and then you get this expression that gives you that the coil size goes to the 3/5 power. So that's 1 over df. So df would be 1.67. And that's what he, where that is. So he gets one. All right, so he says so 1.7 is actually too steep, right? 1.67 would fit this thing perfectly. So that's the odd thing. Like if you numerically integrate it, you get 1.72. And then if you do computer simulations, they get 1.7, which is 1 over 0.588. So you see the 0.588. But the data, when you measure it, is always like 5/3, which it shouldn't be. But I'll show you later on, maybe today, that how Grossberg can get that 5/3 without this assumption that you have to drop off this 3rd term. Right. So in other words, if this is a big number, then the 5th power is much larger than the 3rd. That's what Floyd Kriegbaum said originally. Grossberg does it a little bit slightly differently and doesn't have to make that assumption. So he gets it analytically, kind of gets that answer. So anyway, so that's that one. Oh yeah, there is any other questions on this thing? Yeah. Figure 3 shows. So coarse grain molecular dynamic simulations that reactive groups are close together. Okay, so X is the contour length in that picture, right? So explain what contour length is. So if you have a chain, right? So a polystyrene 100,000 molecular weight, like normal Scotch tape container type polystyrene, the clear stuff that breaks when you squeeze it. So the chain on that's going to be a 10 nanometer. Like if you measure the side, the end distance of the chain is 10 nanometers. But if you take that chain and you could stretch it out totally, it would be like, basically it'd be like 300 nanometers, something like that, right? So it's all kind of in this more compact structure because it's a random walk. So it's going to be like square root of n instead of n, right? So it's going to be a big difference. So anyway, so the contour length is that capital L, that it's like the number times the step length. And so that's the total length of the chain. And then when it's actually convoluted, it'll be much smaller. I mean, like a protein, a native state protein is something like, I think it's something like 100 nanometers. If you stretch it out, it's like a meter. So it's a huge difference, because that's totally collapsed into 3D. So it's just as small as you could probably, but when you stretch it out, it's actually a pretty big thing. And it's atomic diameter, but it's long. Anyway, so anyway, this X is the contour length that he's talking about. So this plot, unless you understand that, you can't make any sense of this thing. So this is how close are these bonded groups after he goes through that routine, right? So you'd expect that the bonded groups, so if you go back to his cartoon, then the bonded groups are a long contour length apart in this case, and they're a short contour length apart in this case, because you're bonding next door neighbors here, right? And here you're kind of bonding things that are far apart in terms of the contour length. The bonding itself is always close together, right? So hopefully that kind of answers it. So that means he's looking to see close together here and far apart here. And that's pretty much what he sees in terms of how many steps along. So it's like 40. And then finally, this one is kind of the size, I guess, of the blob things. I think, what is F? Distribution of distances of reactive units to the center of mass. So this just shows that the reactive units are on the surface. This is kind of the radius of the blob, and the location relative to the center of mass is on the surface of the blob. So this business, if this was actual analytic measurements, that would prove what he has to say. But it's a computer simulation, so you have to think, did he cheat or I mean, it basically comes out pretty much exactly what he wants to prove this cartoon back here. So it is useful, and some things maybe it would be hard to get that. You could get it if you did a fluorescence measurement emissions, like if you tag this with a fluorescing molecule or something, you could get these distances and things. He didn't do that, but that would be pretty involved. He'd have to change the chemistry to do that. I mean, so there are ways you can measure. Also, NMR can give you some of this stuff, like the distances between groups. And he didn't do that either, but what he did was pretty complete, though, I think, and it's convincing to me. But him or her, I don't know if it's a him or a her, the Chinese name. So I guess that's a her, right? Lei sounds like a her. But anyway, so that's about it, I guess. Any other questions on that? Someplace he says, like, somewhere in here he says he measures the viral coefficient, right? Like A2. Let's see, did I do find here? A2, where is it? Is it here? There's three of them. Where? A2. So he measures, so I said B2 in the is part of the viral expansion for the pressure, right? He's second osmotic coefficient A2. So A2 and B2 are proportional to each other, right? But A2 is a square of the molecular weight. It relates the two together. So you have, the reason is that you analytically measure A2 directly and like light scattering when you get more concentrated solutions. And then anyway, what is this character to measure the solvable philicity? So if A2 is positive, that means that it's a dispersion. When A2 is negative, it's not soluble in it. So he measures A2 and he finds out that it's not soluble for polystyrene, but acetone or something. He's got like a positive and a negative. Negative means it's immiscible. Positive means it's miscible. And you notice the units are not, it would be like size, volume. So it should be volume, right? Or volume per mole. Like if it's B2, it should have units of volume because B2 is like the excluded volume. Right, so it should be, or it could be molar volume. So dm cubed, decameter cubed, to a familiar unit. Divided by per mole would be the units. So this A2, if you multiply this by grams per mole squared, you end up with decameters cubed per mole, which would be the B2 that we had before, just for context. Because you'll see, the reason that he's using A2 is he doesn't feel confident he knows what the molecular weight is to divide it to get to B2. And also, the instrument he's using just spits out A2, right? So you'll see A2 for the second viral coefficient as measured by light scattering, and you'll see B2. And they're kind of the same number. So you need to know the molecular weight of the thing that you're talking about in terms of A2 is telling you how well dispersed something is. What is the something and what is its molecular weight? Right? And the something could be different things, right? So it could be a gas atom, like argon gas or something, or it could be a molecule, or it could be a polymer chain, or it could be some kind of colloid thing floating around in milk or whatever, right? So you still can get this A2 number that tells you how well, if it's positive, it's mixing, if it's not positive, it's immiscible. But if you don't know what the thing is, or if what the thing is changes with concentration, it's another possibility. So basically you'd need to know, basically A2 is the thing you measure if you don't know the molecular weight. If you know the molecular weight, you get B2 because that's in units of volume, which is something you're familiar with. And you have excluded volume, so you can calculate it. Because if you know the size of the thing, you can calculate the excluded volume. It's got related to the volume. Anyway, so he did mention A2. I meant to put that in here somehow, but I didn't. And in the raft polymerization we saw I think the first homework, right? So you can see that this raft polymerizations come up every time people want to do something. They aren't really chemists. They just kind of want a polymerization that's going to work. This thing will work for any kind of vinyl polymerization. We have a vinyl group. And so, all right, that's good. That's all I wanted to say about that. That's okay. All right, so let's see. I've been trying to get liquid nitrogen to freeze a rubber ball, but it's like nobody will tell me where it is anymore. It used to be He had chem stockroom and chemistry.
You can get it at graders.
Yeah, but we have it at UC, you know. Can you get it? Can you just buy it or something?
Are you
Or
talking liquid nitrogen?
Yeah.
Or I thought you were talking.
dry ice doesn't really work because you got to go to like -70 to freeze a rubber ball. And you need to go like -110, probably like well below that. So like glass transition for rubber is like -65, something like that, butyl down rubber. So anyway, you need colder than dry ice. It's good point though. I mean, it could come in useful at some point. It's almost, they're talking about, I was reading this thing, they're selling they have those bullet trains in Japan. And I guess the carts on them, so they've been around for like 30 years now. And the carts, the food carts, like no one buys any food, so they're selling them. You can buy one. One of the food carts from the Shindenken bullet trains.
I know Dr. Shi was using liquid nitrogen for a magnet experiment last semester.
Oh,
so
that's
probably
great.
knows where it is.
All right, I'll ask them, yeah. Because it used to be, all right, it used to be you walk into, the chemistry library and you keep going, and then on the right-hand side, before you get to the tower, there's a room. That used to be the stock room. You could just walk in there and take some. But now it looks like they closed that place. So I don't know where you get it exactly, but I'll ask them. That's pretty good. Thanks. Because I've already asked 2 people. Yeah, nobody seems to know. But that's pretty good because it's pretty neat to see that. I think it's worth doing. But anyway, so here, so here's the I did this last time with the PVME, kind of looked at that, and then the Flory-Huggins equation is here somewhere here. So that's for mixing the 2 polymers. So this is the same as this is from the thermo class. So this is the Hildebrand equation for a regular solution, right? That's the Hildebrand mixing parameter. So this is the entropic mixing of kind of marbles. Basically, you have red and blue marbles. That's the entropy of mixing times temperature gives you the free energy. And you add in an enthalpic term that's binary interactions between the A and B units. And this has the average energy of interaction between the A and B units, defined exactly the same as in the Flory-Huggins. So that should be something like committed to your memory. That's for mixing of anything. This is a picture of that mixing oxides and metals, and they form 2 crystal phases. One's a substitutional alloy, so that they totally mix above this temperature and cool it down. They demix into this vanadium and chromium oxide metal crystals or oxide crystals. Right. So if you plot that equation, so because it's symmetric, and so in other words, XB is XA minus 1, or 1 minus XA. Right. So it's a symmetric equation. You can swap A and B and it's get the same answer. Right. So it has to be centered on 50% here. Also, this is mole fraction. Right. So there's a couple of differences with Flory-Huggins. Flory-Huggins uses volume fraction, and this is divided by the molecular weight to give you kind of thinking about counting molecules, not counting. And again, entropy depends on the number of things, right? So it doesn't depend on how big the things are. So if you're mixing polymers, there's a lot fewer things because they're glued together into a chain. Whereas if it's water going onto, so the water will dominate the entropy if you have a polyelectrolyte in water, right? So anyway, so if you just plot this thing, and this thing depends on 1/T by Hildebrand, and this is basically 1880 or 1870 or something, right? So it's really old. So anyway, if you vary the T, then this thing, because log of something that's smaller than 1 is negative. So this term is negative. So this is a change in free energy on mixing. So that drops the free energy. That's a good thing. So entropy drives mixing. Then this thing's generally positive. If you want to see phase, you have positive here, right? So anyway, so they balance off each other, so you can get negative and positive free energy change on mixing, right? So anyway, so if you plot that equation and vary the temperature, this is 1/T, and you get this kind of behavior, right? So T1 is a hot temperature, and it's this smiley face thing. So that's miscible everywhere, because if you take a composition here, do a small fluctuation, it's always more uphill than downhill. That means it's raised the free energy. So that's not going to happen. You have to lower the free energy. right? And then you need a frown face to get phase separation. In that case, any fluctuation here, always both things go down. That lowers the free energy. So you're going to drive it to two phases. The two phases are more stable than the thing you put in, right? Until you get to the inflection point, which is the spinodal point, right? So within the spinodal, this will spontaneously decompose. That's what the term is, meaning that if you make that, it immediately goes to these two phases that are in equilibrium because the derivative of the free energy with respect to composition is a chemical potential. So those 2 points are in equilibrium with each other, right? And that's in a deep quench, that's T5. So that point is that point, and that point is that point. That's it. T5 is 800 Kelvin. You get so this would be the cloud point. Like when we held it in your hand, it turns white. This is what you would determine, except it would be upside down because phase separates on heating instead. Right. So right, that's the T5 thing. And then as you cool it down, so as you heat it up, then you're going to reach a point where, oh, it's going to either be all single phase or it's going to be so that's a critical point. Right. So spinodal, the inflection point's the second derivative is zero. The miscibility limits, the first derivative, like where these things are in equilibrium, is zero. And then this thing, the critical point, all three of these things, and the third derivative is also zero. Right, yeah.
What is, then, so that expression for delta G is being taken with derivative respect to phi. What is phi?
Oh, phi is X, sorry, I took this from the other slide. It's volume fraction from the Flory-Huggins, it's mole fraction here. It should be mole fraction, and Flory made some arguments on why it should be volume fraction. But basically, it's volume fraction for polymers and it's mole fraction for everything else. So it should have been X, sorry about that. I didn't even notice that, it's like, anyway, so that's how you get this thing. So when you get to this critical point, the weird thing is the free energy goes flat, right? That means if I throw in a composition of 0.4, and then I allow fluctuations to happen, so it's going to go left and right. So I make two phases, one to the left, one to the right. Nothing's changed, like the free energy didn't change any. There's no selector for whether it phase separates or not. It means it's like crazy land, it can do anything at once. So any fluctuation could possibly exist or could possibly not exist. So there's no predictability at the critical point. So everybody wants to stay away from the critical point. Right? It's an important point in the system. Basically, it's not where you want to be because there's no way to predict what happens there. Right? So there's no, like, say you're going to have diffusion or something, everything kind of stops. There's no driving force for diffusion. There's no concentration gradient kind of thing that's going to happen. So it's called critical slowing down. As you approach the critical point, the transition stops happening, kind of things slow down. And so critical slowing down, and there's a bunch of other kind of bad words for critical points. So as you go up in temperature, or you go down in temperature, this thing moves out and that etches out the phase diagram. Two phase in the middle, one phase out here. So that's kind of a picture of this. So Flory-Huggins is exactly the same, except divided by the molecular weight. So because the number of things that are involved here is, in other words, the number of objects that are going to give you entropy is smaller, right? And Flory used volume fraction instead of mole fraction, right? But it looks the same. And he's got this chi parameter, which is exactly the same definition as the Hildebrandt parameter. So we got famous for this equation. Like it's not much of a change really. And then because he's using volume fraction, so if you remember, or may not remember, this is the Gibbs free energy. It's under constant pressure. This is like an experimental free energy, right? Constant pressure. But this is that this system, because it's using volume fractions at constant volumes, that's actually a Helmholtz free energy. So to get the Gibbs from Helmholtz, you have to add PV to it. So if you want to do any kind of calculation with this equation, you have to add PV because the Gibbs is the thing you want to balance out to get the chemical potential. To say like two things are at the same chemical potential, then they're at equilibrium. So that's kind of a twist of this. You'll never see that term thrown in except when you kind of people start doing calculations with it, and they'll just toss that in, not say anything. So anyway, so that's that. They're kind of the same equation. It's something you should be familiar with, but probably didn't remember or didn't care, but then anyway, that's the Flory-Huggins equation. So anyway, so if you put in like NB is 1 and Na is a polymer, so it's got 100,000 molecular weight, then this term kind of is larger than that term. And also you lose symmetry. You can't just swap A and B anymore because the two terms are different. So then you get this skewed, it shifts the curve. Instead of being symmetric like that, it's skewed over towards the polymer end of things, towards the solvent end of things. So this is concentration of polymer, volume fraction of polymer. And then it's going to show the same kind of U shape, but it's basically shifted to the left significantly. Like this high end of this is like 1%, 10% or something. Right. So it's significantly shifted over. This isn't a full scale to 1 here. Whereas this thing goes to 1. Anyway, so from these derivatives, you can do a calculation, you can figure out what that critical temperature is, what the critical composition is. Because you have 3 equations, 1, 2, 3 for the critical point. So, and you have 2 unknowns, the temperature and composition, because B is 1 minus A. So it's 2 unknowns, 3 equations. You can solve that. You get the same answer no matter which 2 you pick. And the 2 things you get is the critical temperature, critical composition. You can calculate actually the entire curve here if you just know the chi parameter. All you need to know is 1 number to predict everything. Like that number rules the whole thing because the rest of these are just fixed equations of the composition. I guess you need the molecular weights too. Basically, if you know chi, you can predict the whole phase diagram. So it's kind of a nice, simple equation. But anyway, TC, if you do that, you find out that it's going to be this theta temperature for infinite molecular weight. So when n goes to infinity, that goes to the theta temperature. This 1/2, or chi equals 1/2, temperature where chi equals 1/2. And then you can get to critical composition, which also has a 1 over n to the square root dependent. So both of these things end up being 1 over n to the square root. So basically, these 2 things are proportional to each other. So it'll be a straight line that's the criticals and goes up to this theta temperature and you reach infinite molecular weight. So you have this kind of weird gap. So you have the theta temperature. You can look it up in the polymer handbook for any polymer. And then your actual phase separation point for a real polymer is going to be a gap below that. Like the theta temperature isn't going to tell you where it phase separates. It's going to tell you where an infinite molecular weight polymer would separate. And you have the actual phase diagram here. So that would be nice, if that works. You have a single phase here, 2 phase down here. There's a spinodal within this, like there's another kind of U-shaped thing within it that shows the spinodal regime and nucleation growth regimes at the sides. So there's another number here. So if you take the coil or whatever the thing is, could be a branched thing, could be one of these things from that paper. So within that thing, it's got a concentration. You take the mass of the thing and divide it by the volume, it gives you a concentration, right? And if the mass goes with the size to the fractal dimension and the volume is the size cubed, then you get like the size to the df minus 3 would give you this critical concentration. So as the size goes up, df is going to be less than 3. So this is 1 over size to some power. It's basically this critical concentration drops as you increase the molecular weight of the thing. And you can also do that in terms of the molecular weight because the volume would be the molecular weight 3 by df. So you get the mass is 1 minus 3 by df gives you this overlap concentration, like where the coils would stick together. Right. So this concentration, you can't dilute below that concentration. That's the point. So because you'll have these things floating around. So you can have less of those things, but the concentration within the thing is fixed. Yeah.
What is a df when mass goes to size df?
DF's like the mass goes to size to the DF. So if you have a rod, it's 1. Like if you make double the rod size, it doubles its mass. If you triple the rod size, it triples its mass. If it's a disc, it's 2 because if you double the size of the disc, it squares the square of the disc size gives you the mass. If it's 3D, it's 3. You can have things like a polymer chain, it's 1.67. It's 5/3. Or it's 2 if it's a polymer coil, right? So it's basically a density. It's a number to get the density. And the C star is kind of a measure of the density. It's like mass per volume. It's the density of the blob. Well, that, not blob, but that kind of thing, whatever you want to call it, the coil. Right, so anyway, you have to put that into this plot, so you can put in. You can put in the C star of this thing, so if it's a Gaussian chain, you see like, if the Gaussian chain, df is 2, so this is 3/2, so 1 minus 3/2 is square root of 1 over square root of n, which is the same, it's like the same dependence as these guys, 1 over square root of n. So this thing, this kind of concentration, so all these things are going to move around with the same power law. Like you can draw this picture and it's kind of, could normalize it by square root of n and it would just be the same plot for everything. Right, so anyway, nonetheless, there's this region, right, below which the phase diagram doesn't exist anymore because it's kind of frozen at that point. But the difference is, if you phase separate here, it's going to go like oil and water and separate into 2 phases. If you separate in the yellow thing, then you got to get this thing this guy's trying to get, like these blob things that collapse down, and they're still floating around potentially, right? So this is like coil collapse here, right? And then you have a 2-phase solution, coil collapse. And this is important because this is seen as a model for how proteins fold, like how DNA and RNA fold and pack into a chromosome, right? Like again, I think the chromosomes end up being like miles long. The DNA folds up so much compactly, you know. So basically, there's ways that biology is seen to like compact down a lot of information into a really small package by this kind of folding process. So people are interested in how that works. And also, like in order for the DNA to be read, so it has to like unravel slightly and then it can read and then ravel back up, right? So you have to have this enormous amount of information. You can store it in a small package and you can access it by this unraveling and raveling thing. So people want to know how that works. They also want to, like in this paper, want to know how to copy that and turn it into like money somehow, like make money by selling something, drug delivery, whatever, right? Because biology seems pretty neat and maybe you can make something that people would buy for it, doing the same thing, or if you could cure diseases or whatever. So anyway, so biomimicry in terms of molecular things is based on that. So anyway, so that's that business. And then so you have these like 4 things. You have a theta state, which is this kind of where you have no interactions, good solvent where it's expanded. This would be Gaussian chain. So you have kind of a region where you can get Gaussian chains. And then you have this collapsed coil, and then the phase separation where you get 2 phases out of this thing. So it's kind of it looks just like this phase diagram, but it has little add-ons that keep adding and adding. You know, so it's like a little bit more complicated than the or oxide phase diagram. So anyway, so there's that business. Then there's this. All right, so that's kind of one thing, and then there's another issue here. So if you look at the specific viscosity, so put that in here somewhere. Yeah, so you measure the viscosity of a polymer solution, right? But when you get down to low concentration, then it's almost all solvent, because you have viscosity of polymer solutions, a solvent, then this intrinsic viscosity, which is a number that says how much do you enhance the solvent viscosity by adding in the polymer, right? So this intrinsic viscosity is essentially 1 over C star. It's like how many, oh, it's C divided by C star says how many of these blob things do you have, like how many are in the system? And the more of those you have, the more the viscosity is enhanced. So these things are displacing the fluid. So you have water, and you have a polyelectrolyte in there floating around. The polyelectrolyte, if the water within the polyelectrolyte is trapped, meaning it's non-draining, I call it non-draining, then it's just a sphere of water entrapped in kind of a jello thing floating around. And that's not going to contribute to viscosity at all. So it's displacing the water. So when you measure the viscosity, you're taking like force per area. So it's basically got something to do with the volume of the system. When you put these jello things floating around, what do they call them, the Chinese, when you get the tea with the blobs in it?
Oh, the boba tea.
Yeah, boba tea. So it's like boba tea, except on a nanoscale. So it's displacing the liquid. So basically it's going to boost the viscosity just because you don't have as much liquid in there. In other words, it's as if your system is smaller, you're pretending that it's larger. That means that the viscosity goes higher, right? So that's what this That's basically what this equation says, like, this is just a displacement equation, like you say, the volume of these blobs, concentration divided by that tells you how many blobs. That's gonna change like how much, that's gonna boost the viscosity of the solvent because you displace the solvent with the blobs. Right, so linear sum displacement law. Anyway, so this, what's called intrinsic viscosity isn't viscosity at all, it's 1 over c star. It's got nothing to do with viscosity, even though you measure viscosity to get it, it's really 1 over c star of this thing, right? So, right, so to get that, so you take this equation, and you subtract off the first term, the solvent, you get the reduced viscosity. And then this is going to be the solvent times that thing. So you divide by that, you get the specific viscosity. That's what he's plotting here. So this thing should be like the amount of solvent that you've enhanced it by. In other words, if this thing, if your thing matches the solvent viscosity, this thing goes to 0. And when this thing is 1, you've doubled the viscosity of the system by adding your boba balls into it, right? And then when this thing reaches a value of like, I thought it was a value of 1 is where you saw this transition, but not in this plot. And so 1 is here. So it should be when that reaches 1, that's where you see the entanglement showing up. But these are for polyelectrolytes, so it's probably a little different. Anyway, so the intrinsic is going to be, what would be that boba ball concentration within the boba ball as the concentration of the system goes to 0, because that would change a little bit with concentration. So basically, let the concentration go to 0, take that thing divided by concentration, you get this thing, this intrinsic, which would be this actual boba ball, 1 over the boba ball C star thing, right? 1 over C star would be this thing. That's kind of how, in a nutshell, this viscosity thing works. But so this brings up this thing, like, so it should go as a power 1. It doesn't for these polyelectrolytes. It should go as a power 1, and then it should take off to a power 3. For these, it doesn't in this paper, but basically it should go 1 to 3. And then the cutoff point is where you have, that's the definition of the entanglement, like the weight where the boba balls have hooked together. I mean, they're making a net, we're starting to make a network, and that's why the viscosity shoots up. Right, so you'd think that that number would be the same thing as this C star. In other words, when you saw that upturn, that would, and originally this was kind of how people measured C star because it's easy to do. You take polystyrene, put it into like toluene, then it's like a solution, all of a sudden it becomes napalm up here, right? So then it shoots up. The napalm stuff is more viscous, it sticks to the skin. That's what they used to say in the protests, you know, that, so, or they said it sticks to babies. That was the 60s protest about napalm, made by Dow Chemical, but not that you guys shouldn't co-op for them, but you know, actually a lot of companies made napalm. It wasn't just Dow, but they did get most of the protests were against them. But anyway, that said, so that this is the transition between those things. So it looks like it would be the same thing, but it turns out, all right, so the difference is like this is a static measurement of the coils, and this is a dynamic measurement. So if you start shearing the stuff, this entanglement molecular weight is going to change, right? So that's kind of an issue about what exactly is this thing that you're looking at? Like, how do these things compare with each other? Like a dynamic measure of coil interaction and a static measure of coil interaction, right? So the things, and then, all right, so anyway, so that's what, there's a lot of studies about, not a lot, but there's a few studies about how that kind of works out. This thing is measuring this entanglement molecular weight measured that way, and also the C star measured with light scattering or something, I think. Doesn't say how, I don't remember how C star is determined here, but it's by scattering. And then the CE is determined by this transition, right? So this is kind of an interesting paper. So, and it's important. I think this is a really important paper, even though probably you'll never see it in a book or anything, right? But basically, it's by Colby's the guy that wrote the book on polymer physics, right? So anyway, so the red circles are neutral, like polystyrene and toluene, right? Neutral, good solvent, entanglement, and the red stars are good solvent, C star, right? So, and how do they behave with molecular weight? So CE follows a 0.8, which would be the 5/3, right? In other words, let's see, 0.8. 0.8, oh, here. If you plug in the 3/5 here, you get 0.8 for this C star number, right? And then CE follows exactly the same dependence, meaning that they're the same thing for styrene and toluene. But it isn't styrene and toluene, it's something. Oh, it is polystyrene and toluene. So it is actually napalm he's looking at. So there, all right, so that's nice. Then he takes a polyelectrolyte. So he takes polystyrene sulfonate, which is used for like battery separators. So you take the same polymer, put sulfate groups on the styrene, then it makes domains in the solid state that conduct electricity through it. All right, so you have ionic conductor membranes with that. So anyway, he puts it into solution, and he's got, so basically the blue are polyelectrolyte, the entanglement molecular weight thing. It's like that measurement, like finding where the cutoff is there. Then these are the C star, and that follows a power of -2, which would be for a rod. So there's a polyelectrolyte straightens out into a rod, and the static measurement tells you they're rods, right? And the dynamic measurement, which showed you exactly the same thing for polystyrene and toluene, all of a sudden shows you that they're not rods, they're -0.8, meaning they're expanded coils. Right, so that doesn't make any sense. Like that couldn't possibly happen, right? Because they have to be the same thing. The point is that he comes to, which totally makes sense, is that this measurement, when you do this, is a bulk measurement, like is a measurement on milliliters of this stuff, right? And the other measurement is on like nano, whatever, pico, very small sizes, right? So when you look at this polyelectrolyte on that large scale, these rods actually kind of hook up, right? And they actually form a network that's a good solvent network that has the 0.8. So because the rheology measurement is a bulk measurement, it sees that polyelectrolyte mess as a good solvent mixture of random walk coils that are hooked together, the random walks being made up of rods, right? And then when you look at a small scale, you see rods. So it means that it's misleading to say that the CE and C star are the same number, even though conceptually they are, right? Because one is actually a bulk measurement and one's a nanoscale measurement. That's one problem with CE and C star. The other problem is this business of when you start orienting the chain. So the static measurement is with no flow, but if you start doing things like, so this is called a shadowgraphy, depending on how you pronounce it, which is basically take a glass cup, shine a light through it, and take a picture of the shadow of it. Right. To look at flow, it's kind of useful, especially if you use cross polars. You see the oriented chains light up, and everything else is black. So this is under cross polars. Black means that there's fluid in the black, but basically it's not oriented, and the stuff in the middle is oriented. When it gets to be a very fine fiber, then it becomes bright. So he's making, what he's doing is, this is basically dripping maple syrup onto your pancake. So it starts out with a thick stream, it gets thinner, then it turns into just drops of maple syrup on the thing. You may have seen it. This is actually a science study of maple syrup kind of thing, except they're using polyethylene oxide. That's our water-soluble polymer, right? PEO, polyethylene with the ether groups in it. Anyway, so when you do that kind of measurement, so it's called extensional viscosity. So it's kind of like when you take chewing gum and pull it, right? So and that measurement has this technical problem. Okay, if you want to have a constant strain rate, so you want to have a constant drawing rate of something, then you end up that you have to draw it exponentially increasing in time. So you start out slow, and eventually you have to start really running fast with it, and then put it onto a rocket at some point to get a constant draw rate on it, right? So if you want to get what's called the Troughton viscosity from that, which would be the viscosity that has to do with this extensional flow, you have to invent an experiment where you have an exponentially increasing rate of draw, which isn't possible, right? So people have tried to figure out how to do that by shooting a fluid into a spot and then having it go out in the two directions. Right, so you have like a cross-shaped flow thing with two out and two in. And then right at the center of that, you have constant extensional flow. So there's rheometers that do that. I mean, there's a bunch of things that people have done to try to mess around with it. Anyway, so turns out though, that for a Newtonian fluid, this extensional viscosity that you could measure if you could dream up an exponentially increasing rate of draw. It's just 3 times the normal viscosity. Right? So 3 times the viscosity gives you this extensional viscosity. I mean, this comes into play too if you're doing like spinning fibers. Like we've done this in the lab. I used to do the polymer processing thing. So we do that, and you could see, like if you try to keep a constant kind of draw on the fiber, like you actually, and you pull it out of the extruder by hand, you actually have to like start pulling slowly, and then actually by the end, like run across the room with it so it doesn't like droop down. You know, so it's, I mean, I think it's kind of interesting, the manifestations of what an exponential increase in time of a rate of experiment would be. Anyway, so that's kind of, anyway, so that measurement, so it turns out like this overlap, if you measure the entanglement molecular weight for this kind of overlap experiment, you don't get the same thing. You get kind of deviations in it with extension, because the things are kind of because of this, the fact that the chains are, they'll entangle much earlier when they get drawn out because they're larger. Right, so you see the effect at a much lower molecular weight than you would if it was just a C star. So the extensional thing is anyway, that's just an aside, I guess. But anyway, next time I'm going to talk about the collapse thing, like this this business of the coil collapse, which is based on this Grossberg thing. There's a Grossberg book if you want to look at it. It's kind of interesting, but actually it's on the web page. You can click this link on the top and on slide 40. But, all right, let me quit. What? Try to get the liquid nitrogen. That'll be pretty cool. Oh, wait. There's, all right. So tour on Tuesdays, some Tuesday at Lyondell, 8 o'clock in the morning, 8 to 11. Anybody possible for that, or one? I have one. Okay, I have one taker. I mean, she said 8. She said Tuesdays were great because they have everything's like flying and all the machines are running. It's 275 and 71, right where they cross.
Would it last like
In Fields Erdel or something, whatever that is. Not Fields Erdel, the one before that. Not far from the hospital, yeah.
Would it last about 3 hours? A lot of us have a class that starts
At what?
at 11.
Yeah, we can get out. If we start at 8, I mean, we'd be out by like 9:30 probably, I guess. It depends when we want to start, I think.
Well, where was that? Who did that?
Just Lyondell Basell, Lyondell Bassell. Yeah, okay. All right. But there's possibility that someone was going. All right, that's good.
That's early, but
Yeah.
we'll see.
Well, these industrial guys, you know, they like early.
Yeah, they're usually up at like 6.
They're in there at 6, turning the cranks and stuff, you know.
A good chance.
By 8, they're taking a coffee break. You know, it's like, right. All right. All right, it sounds like we got 3. It's pretty good. And the person that works there. So